So the next step is to actually find the value of lambda that maximizes this coefficient of performance. And in order to do that, we take the coefficient of performance and we differentiate it with respect to lambda. So this gives us the differentiation, the derivative of Cp with respect to lambda is 1 minus 2 lambda minus 3 lambda squared by half. We equate this to 0, we rearrange, and we end up with these two possible values of lambda. So minus 1 is meaningless in this case, doesn't really have any physical significance. It's meaningless to say that the value of d is the opposite of v. So when the wind is blowing in this direction, Vd is blowing in this direction. That's meaningless, it doesn't have any physical significance. So we end up with the value of 2/3, which means that the maximum value, the maximum coefficient of performance takes place when Vd is 2/3 of v. So when the wind drops from this point to 2/3 of its value downwind, that is actually that's when the maximum possible extraction of power of the wind takes place by the blade. And in fact, if you calculate Cp at this point, so the maximum value of Cp is equal to 59%, and that's when lambda equals 2/3. That's when the maximum, and that is actually the maximum possible coefficient of performance that any wind turbine can achieve. It doesn't necessarily mean that that's what will be achieved in practice. In reality, the inefficiencies inside the wind turbine will reduce this further, but this is actually the maximum possible